Hi, this is Mohammed Alshpool. I'm a PhD student at NC State University. In this short video, I will highlight the main points about our paper, Simplifying Persistent Programming Using Battery-Backed Buffers. This is one of the works that investigates non-volatile memories. These are interesting devices due to their attractive features. They are faster than disk, denser than DRAM, and the fact that they are non-volatile means that they can be used to make a non-volatile main memory or persistent memory which should host data that can survive across crashes and reboots. However, these non-volatile memory technologies suffer from some important drawbacks. They are slower than DRAM, especially for write operations. They also have a limited write endurance, which affects their lifetime compared to DRAM. The third challenge we will talk about today, which is the one we will be focusing on throughout the rest of this presentation, is that utilizing the non-volatility feature we talked about in the previous slide introduces significant programming difficulties in order to maintain crash recoverability. In this slide, we will talk about the memory persistency ordering problem to better understand the programming challenges we talked about in the previous slide. In any multi-core system, there is a point, we call it the point of visibility, which is usually in the caches, where any update that crosses this line and be accepted and allocated at the caches will become visible, after getting all the coherence permissions and memory consistency ordering requirements. Similarly, with non-volatile main memory being introduced to the system, any update that reaches the non-volatile memory or even its memory controller with ADR will be considered persistent. Therefore, there is another line in the system, we call it the point of persistency. The issue is that we now have a volatility gap between these 2 points, and moving updates to the point of persistency is driven by the unpredictable natural cache evictions. Therefore, it is very likely that the order of updates arriving at the point of visibility to be completely different than when arriving at the point of persistency. This can cause the memory to be in an inconsistent state when we recover from the crash. One of the most common ways to solve this is by asking the programmer to add special instructions to enforce the ordering of updates arriving at the non-volatile main memory. However, this solution is known to be very tedious and error-prone. And there are other works that tries to solve this issue, but almost all of these works share an important aspect, which is that they are trying to solve the problem by facilitating the movement of updates from the point of visibility to the point of persistency. In contrast, in this work, we try to solve this problem from the other way around and move the point of persistency itself up to be aligned with the point of visibility. If we do that, we will no longer have a gap between these 2 points, and any update being visible will automatically and immediately becomes persistent, which will remove the burden from the programmer to add any special instructions for persistency. But now the question is, how can we align the point of visibility and the point of persistency in the system? There is actually a simple way of doing this, which is by removing the volatility gap and making the entire cache hierarchy becomes non-volatile. And therefore, any update allocated at the caches and becomes visible will also become persistent at the same time, which will simplify persistent programming since there is no longer need for programmers to add special instructions for persistency ordering. The most straightforward way to do this is by implementing the caches in the same way we did for the non-volatile main memory, using NVM technologies like PCM. However, this means that the caches will inherit all the NVM side effects we talked about earlier, which makes this approach not very attractive. Another way to make the caches become non-volatile without the NVM side effects is by using the battery-backed SRAM caches, or EADR. The battery will guarantee draining the caches to the non-volatile main memory when the crash happens, and therefore they will be effectively be considered non-volatile. However, draining the entire cache hierarchy is expected to require adding huge battery to the system, especially since the energy source need to be provisioned according to the worst case scenario where all the content of the caches need to be drained on the crash. Therefore, even EADR approach might not be very attractive either. Because of that, we present our solution battery-backed buffers, or BBB. The main idea is to add small battery-backed persist buffers next to each L1 cache, which will be used to hold persistent updates going to the non-volatile main memory domain. At the same time, they become visible. Our solution requires a much smaller energy source compared to EADR. This is because our solution only needs to drain the buffers at the crash, and therefore it doesn't need to provision the energy source corresponding to the entire cache hierarchy as an EADR. Any update will be allocated at the persist buffers when it becomes visible. And since any update allocated at the buffers will be considered persistent because they are battery backed, our solution aligns the point of visibility and the point of persistency and provides all the programming simplification advantages as EADR, but for an extremely lower cost compared to EADR. In our paper, we evaluated the draining energy and time costs for our solution and EADR. We found that BBB costs from 300 to 700 times less draining cost compared to EADR. We also used Gem5 simulator to evaluate other aspects of our solution and EADR. We found that our solution with only 32 entries introduces only 1% performance overhead and 4.9 number of writes overhead compared to EADR. Furthermore, these overhead can reach almost 0% using persist buffer of size 1024 entries per core. In summary, in this paper, we introduced BBB, which relies on adding battery-backed persist buffers next to each L1 cache. These buffers will be used to hold persistent updates and align the point of visibility and the point of persistency. Our solution provides the same programming simplification advantages as EADR, but for much lower cost. In this paper, we evaluated the best size for the persist buffers, and then we used that size to conduct energy and time costs comparison between EADR and BBB. We found that our solution with only 32 entries per core can provide performance comparable to EADR while requiring significant lower draining cost compared to it. Thank you.